Hi friends, welcome to a quick overview of GPS. This part is originally a part of the course I used to teach on GIS and engineering. Now I'm using this for my intro to transportation engineering class because we're going to use GPS receivers for a couple of projects in the lab. So I hope you get a quick and dirty overview of how GPS works. Actually, I don't need to impress upon you how GPS has taken over our lives, especially in route guidance and navigation on your smartphones as well as in your vehicles. So this used to be like 15 years ago, this used to be non-existent pretty much. Now this is the prime example of GPS and GIS integrated into our lives. GPS gizmos are essential for numerous engineering applications, especially civil engineering applications. And that's what I'm going to focus a little bit on here, not on the navigation part of it, which obviously you will get an idea how this whole thing works for navigation. So what you should know, therefore, is how GPS works. Your lives are intertwined with GPS these days. GPS was originally designed and developed for the US military use only, exclusively for the US military use. In the early 90s, soon after the Gulf War I was won, uh, then President George H.W. Bush Sr., his administration adopted this defense conversion policy. And then they chose to put GPS in use for civilian purposes. And it took a little while, maybe a few years, like 3 or 4 years, and then there was an explosive growth of GPS in the late 90s, which is when it was used exclusively for different purposes. There were uh, GPS receivers, GPS receiver based things have come out, but they were not coming into navigation until probably 2004-ish. In 2023, GPS products and services, not including the smartphones, is approximately $3 billion. Today, they are extensively used in surveying, agriculture, construction, you name it, in every place. The embedded chips in GPS, they're used in a host of mobile electronic devices. So I'm going to quickly run on the generalized civilian GPS uses. First and the foremost, it tells you where you are, and it's precise, and it's very precise for scientific work, especially navigation related. And we know the navigation not just in your car GPS. It used to be only or majority used by the sailors and airline pilots who use GPS for landing and takeoff, even navigation. And you can track things, the fleet, emergency response, everything by using GPS. You know where they are, we know where a bus is, and you can map by just collecting data from using GPS devices. You can map them on, well, in whatever shape or form you are using. The little known facts, little known to the general public, is that GPS devices have very precise clock because everything that GPS devices compute are based on precision timing. The beneficiaries of precision timings are astronomers, power companies, computer networks, communication systems, banks, etc. And I'll give you a couple of examples. One investment banking firm uses GPS to guarantee their transactions are recorded simultaneously at all offices around the world. And that is possible with GPS timing. And a utility company manages their 14,797 miles of transmission lines using GPS timing, accuracy of the GPS timing. So what comprises of GPS? There are three main components. A constellation of 31 Navstar satellites. It used to be 27, now there are 31. And an extensive ground control segment. It's also Earth monitoring control, which includes 6 monitoring stations on different locations on Earth. individual GPS receivers. These are the ones that are in your smartphone. An individual receiver is a passive element of the system, meaning, think about it, your TV set does not talk back to the tower, or your radio doesn't talk back to the tower. Whatever the tower relays, these TV and radio sets receive, and then they kind of let you hear or see things on the sets. And the receivers interpret the satellite data and tell you where you are, and from there your applications can take you places. The Navstar satellites, it's only needs 24 satellites, and others are spares. They orbit the Earth around nearly 13,000 miles, actually 12,600 miles above the Earth. That's approximately, I would say, half the perimeter of the Earth. They're deployed in 6 evenly spaced orbits, and each satellite orbits at speeds that help it pass the monitoring stations every 12 hours. At any given time on Earth, if you look up, and you will be looking at, well, you won't be looking at, there are at least 4 satellites that are visible to your GPS receiver. And they continuously transmit signals on 2 L-band frequencies like L1 and L2, and they use pseudo-random scrambling. I don't completely understand what they mean, but I take their word for it. Control segment is extensive and it is spread throughout the world. For example, there are 6 monitoring stations in the Earth control segment, and they're spread around the world. Ascension Island, Cape Canaveral, Colorado Springs, and the reason I underline that is Colorado Springs is where master control station exists. Diego Garcia, Hawaii, and Kwajalein Island. These are all the places monitoring stations exist. The global positioning system. So here is how it works. The satellites are deployed on an evenly spaced orbits, right? These 6 orbits, and they are visible in the sky at all times. At least 4 are visible at all times. And the satellites, Earth monitoring stations, what happens is the satellites transmit continuous radio signals to the ground receivers at the monitoring stations, and the monitoring stations send correctional data to satellites, and which are then received by GPS unit, and they decode that information and find out where the GPS unit is located, and that is the primary function of GPS unit. Let us see how all these components, the 3 main components, work together. So the entire computation of your location is based on a simple principle that distance traveled equals time times velocity, where the time is the time it takes for the signal to travel from satellite to the receiver. Remember, the GPS satellites and your GPS units have precision clocks. The GPS satellite is sending its own location and the time at which the signal was sent, and you know the velocity of the signal, how it travels, and knowing these variables, you'll be able to compute the distance from that satellite to your unit. And with a perfect clock and known distance from the 3 reference points, you can locate that point, meaning know the coordinates of that point. This process is called trilateration, also known loosely as triangulation. A 4th satellite, of course, if it is available, it makes the measurement more accurate. The 4th satellite also helps you fix the elevation, and meaning if you want to know the elevation of your point, you need the data from the 4th satellite. So at the receiver end, how this component works is the receiver reads the radio signals from 3 satellites. Each satellite position and the time of signal is known, and the receiver computes the distance, and it determines its own location in latitude and longitude. and does triangulation to find the location. Of course, some people call triangulation, but triangulation requires angles, straight lines. So there are no angles involved here. That is why the correct word here is trilateration. Let me demonstrate this trilateration with a simple example. I did my PhD in a university in the located in the southeastern United States. And I will give you a reference point. So it is approximately 300 miles from Memphis, Tennessee. So it could have been anywhere in this blue circle, close to Louisville, Atlanta, New Orleans, right on New Orleans, Tulsa, Oklahoma. But I also give you a second reference point, and it is approximately 155 miles from Atlanta. Mind you, this is great circle distance, not the road travel distance, great circle distance from Atlanta. So that narrows down the search to within this green circle. And I give you a third reference point. It's 180 miles from Charlotte, North Carolina. Bingo. The town where I went to college is Knoxville, Tennessee. And if you just replace these cities with 3 satellites, and those satellites sending satellite M position, satellite A position and time, and satellite C position and time for a receiver in Knoxville, Tennessee, you will know where Knoxville is with reference in absolute location of Knoxville, Tennessee. And this is the principle at work here. Let's see how the same principle works in space, I mean coming from satellites. And here are the 3 satellites in space with reference to that red cross point. And if you get a signal from one satellite, you know it's say it's about 11,000 miles. You know it's somewhere in the sphere, the Earth sphere. That's all it's going to tell you. And the second satellite narrows down our location to that red highlighted place. So it could be in one of these 2 places. It could be in the northern hemisphere, or it could be in the southern hemisphere. And if you go back and do the third signal from the third satellite, and bingo, you will know exact location on Earth where you are. So here are some of the essential things you should know about GPS. It's all about precision clock, and time has to be precise to the nanosecond. If you have an error of 1/100th of a second, it means about 1860 miles of distance error, which is enough to put you on an entirely different continent. And the satellite clock precision is extremely important, but because these are very well controlled, deployed, and managed by the US military, and you can assure about the satellite clock precision, but they use atomic clocks. But your receiver clock is entirely different thing. It depends on the manufacturer and how cheap they are, how expensive they are, etc. So if your receiver has a clock error, and then you have a problem with it. So that's why some of these GPS devices, they are exclusively used for surveying purposes. They're very accurate compared to probably what's in your smartphone. So there are other things you should know. There is no such thing as error-free transmission. And well, for one example, the weather could affect the transmission, and therefore there may be some errors introduced because of the other weather. Also, there is no such thing as perfect clock. So you have to know these limitations, and then there are ways to make the corrections for any errors that might have been introduced into your data. There's a lot more to be covered on this topic, but I will stop here because I want to limit this video for 15 minutes. Thank you for watching.